Today we will be dealing with a topic that is very much central in physics, and that is forces. All right, so you could say it's one of the concepts or topics that actually bring life into physics. When you're talking about a number of things that happen, because from forces you continue and then you get something that we call energy, and energy is very fundamental in physics. So forces are sort of one of those cornerstone topics, if you may think of them like that, or they're just, you can say, just they are very important topics in physics that we have to understand and that we have to deal with. Forces not as complex as you would deal with them when you're talking about classical mechanics. Like there's a course that is called classical mechanics. So, but this one is just like a metric level, and then also it is first year university level. Then that should be okay in dealing with these systems and introducing the concept of forces, right? So the first thing is, what is a force? Okay, so it is enough for us to define. So for instance, if I have a person and the person is just standing still, now if another person comes in and then they just push this person, all right, so what you expect is that this person is going to move, this person that is in front is going to move in that direction. So the question is, what made him move in that direction? Is because he felt something, he felt a push. And this push that is actually feeling is actually what we call a force. It is also possible that you have a person, and then this person, there's another person that is facing this way. I know the hand is too long, right? So this person starts actually going that way. Uh, there's another leg. I know these legs are very strange, right? So what is happening is that here at the hand of the second person, the person is actually feeling something, and that thing is making this second person move in that direction, and this is a pull. So therefore it's enough for us to just define forces as a pull, not forces, we can just say a force or a push. Okay, so anything that is pulling or anything that is pushing, there's forces. So whenever there's pulling, pushing, then there's forces. All right, then of course they do different things in different systems, but whenever there's a force, whenever there's a pull or a push, there's basically forces. So let me just erase this. Right, so that's what a force is, a pull or a push. That's basically it. That's what a force is. Okay, now it turns out that when we actually do some investigation of this type of a force, you will understand that it depends on the direction that this push and pull is actually applied. So first of all, if I push the person but I don't actually have a very large amount of a push, meaning that I'm not pushing too hard, the person may move, but they're not going to move as fast. So, but if I push harder, they are going to move very fast. So, which means that how much I apply my push, if I may put it like that, or how much the quantity of my push actually has play into basically the forces, the force that is going to be felt by the person. So which means that the size of the force matters. Another thing is it depends on the direction that I'm pushing the person. If I'm pushing the person in this direction, um in this direction, I expect this person to actually go in that direction, right? Because I am pushing them in that direction. So which means that the force depends on two things. It depends on the size. So this size is also known as the magnitude. So you would be aware, because I've done vectors with you guys, and there are videos, you can go and watch those videos on vectors. And it also depends on the direction. Okay, so already we know this, that if something has size and direction as something that is playing a role in that quantity is a vector. So which means that force is a vector. Okay, so it means that force is a vector, and if force is a vector, then it means that we can do everything that we do with vectors, we can actually do with forces. And this allows us to actually be able to treat our forces mathematically, right? Okay, so how do we represent them? That's the thing. All right, so how we represent them, let's say assume that I have a mass, and my mass has mass m, or my object, let's assume I have an object with mass m, not the mass with mass m. Well, you can't say that, sorry. But then let's just say I have an object and my object has mass m. So I could apply a force in this direction. So since it's a vector, it's going to have a head. So this head is telling me that what direction is this force being applied. Now this line here, depending on how long it is telling me how big that force is. So for instance, if I could say that this force, the magnitude of this force was going to be 2 newtons. Let's say, for instance, let's call this force F, and we say that the magnitude, remember when I did vectors, I said that if I just write F without this arrow thing, I'm saying just the magnitude. Okay, so just the magnitude of this force, it is going to be 2 newton. All right, so okay, so if I represent 2 newton like this, the question is, if I change my force and now I make it 8 newton, same direction, how would I represent it? Well, I will still have the same object m, but because this 8 newton is going to be longer, meaning that I am going to show that the size is bigger by making it longer than the first one. In reality, it should be 4 times the first one, because 8 is 4. If you say 8 divided by 2, you'll get 4, which means that 8 is 4 times 2, is 4 times this force here. All right, so this would be my force for 8. So this is how we represent forces. We represent them as vectors. They're going to have a tail, there's a tail. They're going to have here, they are going to have the head, and there's the head here. All right, then that force is applied on this mass, which means that it is going to be felt by this mass. All right, and remember, since we said that the forces are vectors, means you can do a couple of things. Remember with vectors, so it means that if I have two forces, let me say I have two forces, so one person is pulling this object that way, and the force is 4 newton. Then the other person is pulling it that way. Let's say this is force 1, and then let's say that this is force 2, and force 2, let's just say 7 newton. I can find what I call the resultant force. All right, now this resultant force is also known as F net. Okay, so it is a vector. It is going to be given by all the forces that are acting on this object. So on this object feels the force that is pulling it that way. So one of the force that is acting on the object is going to be F1. This object also feels the force pulling it in the other way, and that is going to be F2. Now here's the most important thing. You need to choose the Cartesian plane. So you need to tell us what side are you taking as positive and what side are you taking as negative. all the time. Now for this course, I'm always, unless I specify otherwise, I'm always going to take this side as x and it will be positive. Then I'm going to take this side as y and it's going to be positive. Now I normally prefer to just put unit vectors, meaning that I'm just showing the directions of unit vectors, but it's fine for this course. Sorry about that. For this course, I'm just actually just going to leave it like that. Okay, it's just going to be x and then it's going to be y like this. All right, so that's good, that's fine. So I know the direction, so which means that any force that is horizontal, if it's facing the right, it's going to be positive. If it's facing the left, it's going to be negative, which means that anything that is facing that way is going to be negative on the x. Anything going that way is going to be negative on the y. All right, so that's basically what it means. So if I look at these two forces, the magnitude of F1, it is going to be 4. And now the direction of F1, is it positive or negative? It is positive. All right. Now this plus, I'm going to write it plus. All right. So I'm just going to write it as plus. Now F2 is 7. Is it positive or negative? It is facing to the left. Therefore, it is going to be negative. And then the brackets. Now this is going to be plus 4 is the same as 4. Plus multiplied by minus is going to be minus, then 7. So the answer, which means that my resultant force, it is going to be minus 3 Newton. So how do I draw this minus 3 Newton? It means that the resultant force is going to be 3 Newton. The size, how big is it? The force F net, let's just say, let's call it F. All right, we can call it F, we can call it FR, it's up to you. Some people say FR for resultant force, they can call it F. I might call it F going forward, or sometimes I might call it F net, it just depends. And this is going to be facing that way. Why is it facing that way? Because F is negative, and I said anything negative is going to be facing that way. And I know it's on the x-axis because both of these forces on the x-axis. We are going to deal with forces that are not on the x-axis now. All right, so this is how you can actually find the resultant vector, the resultant force, which is the resultant vector. All right, if you have more than one force that is acting, so which means that this object, if this object was moving, this object would actually move in this direction. That's how this object move in that direction. You will get to understand later why we're saying that this object is going to move in that direction. Okay, all right. Now, since these are vectors, the question is, can I find the forces when there's some forces on the x and some forces on the y? All right, so let's take the same problem. So I have the same problem. It has mass m. So you remember I said that F1 was 4 Newton in that direction. All right, so I'm not gonna put the arrow because I'm just telling you that the magnitude of this force is that's why I'm not putting the arrows on top. And then F2 is going to be 7 Newton. Now let's just say there's something that is also pulling this object up, and let's call that F3. And let's just say it's pulling this object up with the force of 5 Newton. Now the question still stands, what is going to be F net? All right, which is what is going to be the resultant force. Now remember, the resultant force is the sum of all the forces that are acting on this object. Right? F net is always the sum. Okay, so the question is, what is the sum? Well, the sum is going to be force 1. I'm putting it because it's vectors here, and I'm also saying it is still a vector, F2, and then I'm also saying it's still a vector f3. So when it's still a vector, you don't put plus or minus because it's just a vector. The plus and the minus is inside the vector. You will see now. All right. Now this one is going to be f net, still a vector. Okay, and then let me see, f1. So where's f1? F1 is positive 4. Now, because I have an x and a y, what I will do is I will specify what is x and what is y. Again, go and watch the chapter on vectors. And then this is just a unit vector in the positive x-axis, a unit vector in the positive y-axis. So what I'm going to do, as a matter of fact, is I'm going to remove this, and then I am going to do this. So this is going to be 4. There's 4. It's facing to the right. So I'm saying everything to the right is going to be positive x. So I'm going to multiply it by positive x direction. So this thing, this unit vector just says x direction. Just think of it like that. Okay. Another vector is f2. All right. If you look at f2, so we write the plus, there's a plus, so write it. Now, what is the magnitude of x2? It is 7. What is the direction of f2? It is minus x. Okay, so why minus? Because it is facing to the left. Okay, now then this one is going, I'm going to write the plus. This is the plus, right? So these two pluses, you write them. There's the first, this plus is this plus, this plus is this plus. So just write the plus. Don't change these signs yet. Okay, now it is going up and it is 5. It is 5, but now what direction? In the y direction. Okay, so let's see f net again. I think I'm gonna stop calling it f net. I'm just gonna call it f going forward. It is still a vector, so which means that the answer that I will get is going to be a vector. Okay, and then from here, both these are on the x-axis, but let me simplify them. It's going to be 4 in the x-axis minus, where does the minus come in? Plus multiplied by minus, or alternatively you can take out the minus. When you take out the minus, it comes here. Okay, let me just do it so that you can see how I'm doing this. I'm going to take out this minus, put it in front of 7. So what happens is that it becomes minus 7x. All right, and then this is plus 5y. All right, now this is 4x minus 7 in the x direction plus 5 in the y direction. I forgot 5. Okay, this is going to the, where you see the x's, you can add them because they are, all of them are in the same direction as x. So this is going to be 4 minus 7. You can put brackets, and all of those are going to be in the x direction. So this minus is accounted for by here, and then this is going to be 5y. All right, and then from here, this is going to be minus 3x plus 5y. So this is just a recap of vectors. We did all of this thing in vectors. So I'm just showing you that it does work like vectors. All right. So if I wanted the magnitude of this force, so let me call this force F, guys. Let's just call it F because this F net thing is too much to write for me. So this force F, first let's draw it. Okay, if we're to draw this force, how are we going to draw it? All right, so let's see. It is going to be a vector that is in the x direction. There's a vector in the x direction. Now the question is, where is it pointing? To the right or left? It's negative, so it's pointing to the left. That's the first vector. So this is minus 3x. All right, this is like a 3 Newton. All right, actually let's just put the Newton in the x direction. Okay, if you want. Now from the head of that, you are going to join the second vector. What is the second vector? It is 5y. So y is going up or down, but since it's positive here, then it means that this is going to be 5y. Now, if you are in metric, you may not actually need to write this. You could do it differently. If you're in metric, I'm going to show you now maybe how you can approach it. If you're in metric, if you're at varsity, for instance, in my class, because I teach at university, in my class, I prefer students to just get used to this x and y notation. Other textbooks is ing notation. So the resultant vector of the two vectors is going to start from the tail, then to end at the head. All right. So when you do that, you'll find that this is going to be f. This is the resultant vector. And the angle theta that you are going to find will be this. Then when you want to actually find them, now if you look at this, it is forming a right angle triangle, and it will always, when you do this, it will always form a right angle triangle. There's a way we can do it with vectors. This is how we do it in actual fact, but then once you introduce certain concepts, it's going to be a little bit different after that. All right. Okay. So this one, it's a right angle triangle. I mean, if you look at it, it's a right angle triangle. It looks like this. And from mathematics, you know that this side is the hypotenuse is r. So where you see, so r is going to be resemble f, or f is going to resemble r, and then this is x. So which means that this one I can actually call it fx, which is minus 3 Newton. All right. I can call this fy, which is the force on the y-axis. Okay. And then this is fy, which is going to be that. So which means that this fx resembles this x on this green triangle, and then this fy resembles this y in this green triangle. Now I know that when I have a right angle triangle, I can actually use Pythagoras. Okay, so if I wanted to find out what is the size, the magnitude, let me say the question was asking you what is the magnitude, you will say that the magnitude is always going to be given by the force in the x direction square that force. Doesn't matter even if it's negative, you're going to see it now, plus the force in the y direction, then you square it. For instance, for this example, this is going to be a square root of minus 3 because it's minus 3 here, but you are going to square it. So it does, that's why it doesn't matter whether you put a plus or minus, because when you square it, it's always going to be positive anyway. All right, and then this is going to be 5 squared, because fy is 5, the magnitude of fy is 5, the direction is y, right? So this is almost, this is the size, this is the direction. I'll just write direction. This is the size, how big is the force, what is the direction of the force, right? So if there's a minus here, then the direction will be minus y. If there's a plus here, then the direction is up, which is plus y. If there's a minus, the direction is minus down, which is minus y. All right. So basically here is just 9 plus 25, which is going to be something like 34, square root of 34. All right, I'm gonna leave it like that. I'm just gonna leave it as a square root of 34. Okay, so that's fine, that's good. I think we are winning. All right, now from here, what we can do, we can find the direction. So the direction is this theta here. It's this theta here. All right, so I'm just recapping basically what I did with vectors. It is that theta there, and then this is going to be equals to, it's always going to be whatever is fy, always like this, and you take it as positive. Even if it's negative 5, you don't put the negative, and whatever is fx, all right, you don't put the negative. All right, so for instance, if I was calculating it for this, it would be 5, over, see here is minus 3, but I don't put the minus, I just put 3. Okay, and when you do that, you will see that your tan of theta is going to be 5 over 3. All right, so this is going to be 1 point something. So let me just put it as 5 over 3. So if I want theta, I'm going to go to my calculator and say tan minus 1, put whatever the fraction is, then that's going to be theta. Okay, so which means that theta, for instance, is going to be equals to 59.0, so 59 degrees. Remember how the triangle looked? I had fx, and then I had fy, and then my resultant vector was like that, and that's where my theta was, and I said that this is f, so this vector was the resultant vector. Okay, so now this resultant vector looks like this. So the question is, what is the direction of that vector? Now you could say it is 59 degrees, and then what you do is here at the tail of this, you can draw a small Cartesian plane. If you are drawing a small, actually it doesn't even have to be small. If you extend this Cartesian plane, you can see that theta is above the negative x-axis. So you can say 59 degrees above the negative x-axis or x direction, or you could say x, you could say negative x, and then you could say axis if you want, still fine. Okay, so let me just do it like that. So, and then just erase this. There's two ways you can say it. You can say above the negative x direction, or you could say above the negative x axis. Okay, so the negative x axis. Okay, the positive x axis, negative x axis, positive y axis, positive axis. So it should be axis there, which is a. All right, axis, not exit. I don't know why I'm saying exit, axis. Okay, so this is how you can actually find the direction of that. Another way you could say, you know, for instance, you have on north, east, and south. This is north, this is east, this is west, this is south. So you could say, for me to actually move from the tail of this vector f to the head of this vector f, I had to start from the, I had to actually start from the, because theta is here. So in order to get theta, I had to go left, and left is west. Then after going west, I had to go north, and then that's where I can actually combine this. So I went west to north, but when I write it, I'm gonna say theta is going to be 59 degrees north of west. All right, so even here I started west, I started from going from here to west, then I went north. So I went from west to north, but when I write it, I swap it around. Okay, I start with whichever one is ending here, and then I'll say north of west. So you could use any of this. Hopefully your teachers can be happy with any of this, and you shouldn't lose marks because you actually use this. All right, so there are two things now that we have to talk about, and one of it is you will come across whereby, let me say for instance, I have an object, right? There's a good example, and there are so many forces. Maybe there's force F1, maybe there's force F2 going up, there's another force F3 that is going up, then there's another force F4 that is going up, maybe there's another force F5 that is going down. So you can represent forces like this. All right, now when you doing it like this, this is known as the force diagram. All right, so this is the force diagram. Okay, all right, now you could do this, but instead of having a mass, where there's a mass, you just have a dot. Okay, where there's a mass, you just have a dot. And then when you actually do that, and then it is actually something different when you do it like that. Okay, so when you do it like this, there's one force, F1, there's another force here which I said is F5. Of course, now since it's a free body, it's going to be 2. You have to draw it like that. It's also going up, this one going to be 3. Then you have to draw it like that, it's going to be 4. So all of these are vectors, so I must put vectors to show that these are vectors, meaning that they have direction, magnitude, and direction. Okay, so I'm talking about the vector 4, that it looks like that. Okay, so this one is known as the free body diagram. Okay, so this is free body diagram. All right, so these are the two ways you can represent forces that are acting. Don't worry, we're going to get to examples, and then from those examples actually you're going to actually use this. Okay, so these are known as the free body diagrams. Okay, all right, so that is good, that is fine in my view. And then now you are ready to be introduced to something that is called the Newton laws. Okay, so I am not going to write Newton's laws. Should I not? Maybe let me just write them, it's fine. I'll write them. All right, and then so you can take it from when I write them. All right, so the Newton's first law, so how we write this, we just write Newton, and then one, you see this also in a lot of textbooks, so it's just N Roman figure 1. All right, so what does it say? It says that of course there are variations. For instance, some people will say an object will continue at uniform velocity or remain at rest unless a net force is applied. All right, so they will write it a little bit different. So most of the time people are not too fussy about it. Some schools are fussy, so what I would recommend is go and look at your study guides if you're at matric, because matric they can be a little bit fussy about certain things. If you're at varsity, it wouldn't matter that much how you state it, as long as we know that you're stating the correct law. All right, so the actual wording may not be something that we too fussy about. I'm not fussy about. All right, okay, all right, so this is Newton's law. Now this Newton's law introduces us to something that we call inertia. Now what inertia actually is the tendency of an object to resist change. So which means that it is this thing that happens in nature. It's a natural phenomena. It happens in nature. What happens in nature is that objects don't want to be disturbed, so they would rather remain at rest, or they would actually rather continue at a constant velocity. How you see this concept of inertia happening is that when you are in a, let me say there's a car, right? There's a car and there's a person on the car sitting on a chair. So if the car is moving in this direction at 30 meters per second, this person is also moving at 30 meters per second. Now if this car stops, let me just say something happens, and the car just decided to stop. Okay, what happens is that the person doesn't stop immediately. The person wants to continue moving it. So even if the car has stopped, but the person inside the car continues to move it, v is equals to 30 meters per second. So that is why when you are in a car and the car is stopping, you go forward. It's because before the car stopped, you were moving with the car, right? If someone outside the car looking at you was going to see you moving at the same speed that the car is moving at. Okay, more especially because here in this chapter we are not focusing on relative velocities, so we're just gonna take it like you're in a car, you're not moving in a car, you're sitting in a car, on a car, inside the car, sorry. Then when you're sitting inside the car, what is going to happen is that you are moving at the same speed as the car. So when the car stops, the car has stopped, but you don't stop moving, you continue moving. And this is because of inertia. All right. Now, the bigger the mass of an object, or the bigger the resistance of an object, we know that the bigger the mass, meaning that the larger the mass, the more difficult it is for you to change. Let me say, for instance, you have a very big rock and it's just there, sitting there at rest. For you to move it, it is very difficult. You have to apply a lot of force for you to move it. So which means that its tendency to resist change is very high because you have to apply a lot of force to move it, right? And then, but if you have a smaller stone, you are calm and apply the same force you applied on a bigger stone, the smaller stone is going to move, which means that its tendency to resist change is very small. Now, it does resist change, but it's just that it's very small. All right. Now, because it has a smaller tendency, now we actually saying that mass is a measure of inertia. All right, it's some measure of inertia. We just put it in a quantity, we quantify that measure of inertia, and then that actually becomes mass. And this now actually brings us to the second law, right? So I'm no longer going to say it's Newton's second law, I'm just going to say Newton 2. All right, now what is Newton 2? Okay, this is how you actually write Newton's 2. All right, this is how you actually write Newton's 2. So, but then what does this thing mean? Now, mathematically, we are talking about a net force. They are saying that when a net force, so what is a net force? So the best way I can actually describe what a net force is this. Let me say I have an object with mass m. Someone is pulling this object this way, right? And someone is pulling this object that way. This person pulling it here is pulling with 40 Newton. This person here is also pulling with 40 Newton. If I was to find the resultant force, which is the sum of this, if I was to find the sum of all of these forces, it is going to be 40 in the right, this 40 F1, minus this another 40, minus 40, and then because all of them are in the x direction, and then I get that the sum of all the forces is 0. Now, this sum of the forces is actually what we call the net force. Another example would be, let me say I have F1, F1 is 80 Newton, and then I have F2, and F2 is 30 Newton. Find the sum. If I find the sum for the second one, it's going to be F1 is 80, is positive, F2 is minus 30. So you can see that the second one has a sum of all the forces. This sum of all forces it is actually what we call a net force. So it doesn't mean just because you have applied a force on an object, then the object is gonna now has a net force. It's not true. There might be another force that you may not be aware of that is countering, or it is opposing the force that you are applying, and you find that you are trying to push the object is not moving. So the reason why the object is not moving is because there is another force that is actually in a different direction. So that is why I always say, when I explain this concept of net force, it's always better to think of it when you have more than one force, basically. That's why it's better to explain when you have two forces. So the first one, the net force is there, but it is zero, right? So which means that there is no net force, basically. Even though I said the net force is there, but it is zero. Being zero means that there's nothing, there's no net force. But it doesn't mean you're not applying. This person is pushing, this person is pushing. So it's just that these forces are cancelling each other out such that there's no net force. So this object is not going to move. It's going to have a speed of 0 is equals to velocity is going to be equals to 0 meters. How about this one? This one, we can say that the force, the net force, let's call it F, which is the sum of all the forces. This sum of all the forces, it is F, and it is in that direction. So there is a net force on the second case. If this is case A and this is case B, there is a net force on case B. Now, since there's a net force on case B, Newton's tools say that since now there's a net force that is applied on this mass M, this mass M is going to also accelerate in that direction, meaning that it is going to speed up, meaning that it's going to move in that direction as well. And if you check the direction that it's moving with, it's the same direction as the direction of the net force, right? Even though you have too many forces here, but then you need to find the direction of the net force. That is the direction that the acceleration is going to have, not the direction of any force that you apply. So this is going to become clearer as we go along, and we actually start changing we actually start doing a lot of applications. So this is what net force is. Now let's go. So now we understand what is this net force that Newton's 2 is talking about when it says that when a net force acts on an object with mass m. Now we need to understand the part whereby it says that the force is directly proportional to the acceleration is directly proportional to the force, inversely proportional to the mass. In mathematics, what we normally do is, we normally say acceleration. When you say it's proportional, you use this sign. It is proportional to the force, right? And it is inversely proportional to the mass. It is proportional to the force. All right, that is basically what acceleration is, and it is inversely proportional to the mass. So you could actually say that it is basically proportional to 1 over m. All right, so because it has to be inversely proportional to the mass, it should be something like this. All right, now when you actually do this equation, you'll find that the force is going to be equals to ma, which means that A is going to be F over M. So this is why we say that it is directly proportional to the F, inversely proportional to the M. What does that mean? All right, let me say I have a force, a net force, and my net force is 2 Newton. That's my net force. Now the question is, okay, what would be the acceleration? My acceleration will be given by F is equals to ma. That's for this 2 Newton. So I could put 2 Newton here, and depending what do I have. Now, if I then double my force, what is going to happen to acceleration? So let's call this force that I'm doubling F1. My new net force is F1 now. If I double it, I will have a new acceleration. So I'll have to call this acceleration A1. So, but F1 is 2 times F because I've doubled it, right? The force F1 is double the force F. So meaning that F1 is 4 Newton, which is 2 times what F was, all right? So then my mass is that, so which means that my acceleration A1 is going to be equals to 2 times F over M. But if you look at it from this equation here, right, acceleration A was actually equals to F over M. So when I see F over M, I can put A. So which means, now this thing just says which means. So whenever you see me writing this, I'm basically saying which means. That's basically what I'm saying. A1, this A1, it is going to be equals to, this equals to 2 times, which is this 2. Where I see F over M, I'm going to put A. So you can see that if I double my force, I'm also doubling my acceleration. So my new acceleration will be 2 times the original acceleration. And this is true. If I triple it, it will be 3 times acceleration. And that is what it actually meant when they say that my acceleration is actually directly proportional to the force. It means that whenever I double my acceleration, I'm doubling my force. When I'm doubling my force, I'm doubling my acceleration. So it is increasing. As force increases, the acceleration also increases. That's what directly proportional means. It doesn't just increase. It's not just proportional. It doesn't just increase. It is directly proportional, meaning that it increases by the same factor. So which means that if I have a force and I double it, the acceleration also doubles. Or I have acceleration and I double acceleration, my force doubles. If I triple my acceleration, my force also triples. If I 4 over 3 my acceleration, my force will also be 4 over 3 the original force. So whatever value I'm applying on the acceleration is also going to be applied on the force itself. Now, what about this inversely proportional? Okay, all right. So we're gonna do a similar case than the one that we had before, which is saying that F is equals to MA. So in this case, my original F is 2 newtons again. All right. So on this one, my acceleration, of course, is going to be F over M. So I'm going to keep the force constant. Let me just say my mass is 1 kg. Let's just say 2. That's fine. 1 kg. Right? My mass is 1 kg. Now the question is, if I apply the same force on this object, so I'm applying the same force. So in the second case, I am applying the same force. I'm not changing the force, but I'm changing the mass. I'm applying 2 times. So I'm increasing my mass to 2 kg for the same force. What is going to happen to acceleration? Well, I'm going to have a new acceleration. So let's call it acceleration F1. Right? This is going to be F1. This is going to be M1. Okay? So my new acceleration A1 is going to be equals to F1 over M1. All right? This is coming from F1 is equals to M1 over A1. So meaning that everything here is new. But then my F1 and F are the same. Okay, so I don't have to worry about F. So this is the same as F. Where I see F1, I can just say F. And then this is M1. So I put M1 so that I show you that this is a new case. Now what is happening to my acceleration? Well, I'm saying, well, my acceleration A1 is going to be equals to F divided by 2 times what? Mass. Why? Because this 2 kg is 2 times m. This is the same as 2 times m because m is 1 kg. So if I say 2 times 1, I'm going to get 2 kg. So that is why I'm saying is 2 times m. I'm doubling it. So, and then from here you can see that my A1 is going to be half, and then this is F over M. And then if you actually follow this through, you will see that this is A1 is equals to half, and then this one here is actually the same as A, right? So you can see that by actually increasing the mass, what you have actually done to the acceleration is you have decreased it by the same factor, which is 2. That is why you're getting half. If you had increased the mass by 3, then you are going to get 1 over 3 here. So that is why we say it is inversely proportional, meaning that when you increase the mass, the acceleration decreases. When you decrease the mass, the acceleration increases. All right, so let's put everything together, and then so that you have something that is more clearer for you, to you guys. All right, something more clearer basically says that the acceleration increases when force increases. All right, and then acceleration A decreases when force decreases. Also, the mass, the acceleration increases when mass, not increase this case, decreases. So in order to, if you keep the force constant, this have to decrease. And also acceleration decrease when mass increase. All right, so basically that is what it means. Now this equation here that we have is going to be very fundamental. It says that the sum, that is Newton's 2, of all the forces that are acting on an object is going to be m multiplied by the acceleration that this object is going to accelerate to. Now I am putting these arrows to show you that these forces are vectors and acceleration is a vector. So acceleration A is a vector. So which means that everything that you apply to vectors also applies to acceleration. All right. Okay. So I think we have actually managed to group everything together, and now we can actually start maybe working on examples and applying our Newton's 2. But before we apply our Newton's 2, it's very important to understand how we measure force. So force is going to be measured in Newton. So the unit for force is Newton. So basically 1 Newton is equals to the mass, which is kilogram, the acceleration, which is meters per second squared. So basically this is what a Newton is. All right, so we measure force using newtons, the same person that we're actually naming the laws after, newtons. Right, so this is basically what we have, guys, and then this is a very good summary. All right, okay.